Hello everyone, I'm Michel Albonico and I'm going to present the work Architectural Tactics for Energy-Aware Robotics Software, a preliminary study. Robots are becoming very popular in the main worldwide economies, industries and cities. A great part of them are battery-powered, from whom the energy becomes a critical factor. Yet, industrial robots have a comprehensive impact on the energy consumption in industrialized countries around the globe. For instance, it's projected that the industrial sector will increase energy consumption by 44% between 2006 and 2030. This may limit their greenness and impact negatively their international carbon agreements. The software is heavily present in those systems and getting more complex every day, so rethinking its development is a good starting point to reason about how to reduce energy consumption. Before I go further, this study lays on the concept of architectural tactics, which basically are design choices made by software architects that help achieving some quality requirement when the software is exposed to some stimulus. Today, roboticists don't have any reference of how to make their system energy aware, where looking into practice is a good starting point. Therefore, in this work we aim at identifying and documenting existing energy-aware architectural tactics in the state of the practice of robotic software. So we help practitioners in making their robotic systems more energy efficient. For this, we look into thousands of ROS-based software projects. We choose ROS because it's a standard among robotic projects and counts on a vibrant community with thousands of open discussions on the internet. Basically, it provides a set of libraries, tools, and conventions for building robotic systems. Here we see our study workflow, which is divided into 4 main phases. In phase 1, we build an initial data set with more than 300,000 data points by crawling ROS open data sources. In phase 2, we filter the data set with a keyword-based search, which results in 562 data points that are specifically related to energy. In phase 3, we manually identify 97 data points with architecturally relevant discussion. And finally, in phase 4, we synthesize the architectural tactics for energy-aware robotic software via thematic analysis and document a catalog with 7 energy-aware tactics available in the replication package. All these phases can be reproduced with the tools we provide in the replication package, linked at the bottom of this slide. Now let's discuss a bit the result, from where we highlight the 2 most frequent architectural tactics that we identify. We call the first one as energy savings mode. This tactic intends to make the system components aware of energy saving needs when the robot's energy level is low or critical. For that, some projects implement a controller that constantly gets the robot energy state and based on preset thresholds turns the energy saving mode on or off. As you can see in the 2 diagrams on the right, the static is usually implemented with 2 main components, which we call the energy savings mode controller and the observer. The energy savings mode controller works as a kind of blackboard, keeping track of the current energy savings mode and making it available to the other components in the system. The observer is any other component that gets the current mode from the energy savings mode controller and then switches its energy savings mode. This can be verified in the GitHub project linked at the bottom of this slide. The second most frequent architectural tactic is called Stop Current Task and Recharge. Its goal is to ensure the robot completes its task. The solution is to interrupt the task if the robot energy level is low and instruct the robot to recharge. After recharge, the robot resumes its task. In the figures on the right, it's illustrated with 3 main components: the task requester, the arbiter, and the executor. Basically, the task requester requests the robot to execute some tasks. Then, the arbiter checks the energy level of the robot's battery. If the energy level is not critical, it instructs the task executor component to start the task. The arbiter continuously keeps track of the energy level, and whenever it goes low, It instructs the task executor to pause the task and the robot to recharge. When the robot is recharged, the arbiter instructs the task executor to resume the task. We also share a project example at the bottom of this slide. As future work, we intend to catalog all the architectural tactics we found and perform some empirical experiments to understand the impact of such tactics over other quality requirements of the robotic system. Thank you for watching this. Please, we invite you to read our paper so we can deeply discuss it.